Hey everyone, this is Tim. This summer I was an intern at Microsoft, and today I'll be talking about a project that I did during my time at Microsoft called Triton-San, which is an application of LLVM sanitizers to debug Triton kernels. Okay, so recently there's been a trend in Python-based GPU programming languages in the HPC and AI space. Triton is one of these languages and will be the focus of this talk. These languages are known for having a gentle learning curve and their simplicity, yet also being expressive enough to define some pretty efficient kernels. However, like with any language, if you misuse the constructs provided to us, you may introduce some pretty nasty programming errors into your code, and some of these errors can be pretty difficult to detect. Currently, there are pretty few tools available to help programmers detect these elusive programming errors, which we will get into. So I've listed 3 of some challenging programming errors to detect in your code, and these are also the 3 classes of programming errors that our tool Triton-San focuses on being able to detect. They are buffer overflow, use of uninitialized memory, and data races. And these issues are difficult to detect because they often exhibit silent or non-deterministic behaviors in your code. For example, we can consider buffer overflows on the GPU. For GPUs and Python programs, memory allocation on the GPU is a bit strange in that sometimes your program gets allocated a lot more memory than it ever needs. So if the buffer overflow occurs in your program and it occurs within the total memory allocated to your program, there's a chance that it doesn't get flagged and it appears like illegal access, which is why it can occur silently. This means that your code may have some unexpected or unintentional behaviors, and as you can see, it will be very difficult to pinpoint where it's coming from. So our work, Triton-San, aims to detect these elusive issues. Triton-San stands for Triton Sanitizer, where a sanitizer is a dynamic analysis tool that pinpoints such elusive programming errors. And dynamic analysis meaning that the sanitizer does so during runtime. Triton-San's main idea is to leverage these existing LLVM sanitizers. And the reason we do this is because we know they work, and they're reliable, and they're consistently being maintained. However, in order to leverage these sanitizers, we need to offload the kernel execution to the CPU. And this is because these sanitizers are built to be executed on the CPU only. However, this does provide us with some advantages, such as being able to leverage the built-in MLIR and LLVM passes that come in with CPU compilation and are more mature and robust. And we also are able to leverage existing LLVM runtimes like OpenMP to help parallelize our programs that run on the CPU, which will be important later. But first, some background into Triton. Triton uses just-in-time compilation. So to go over this a bit, basically the Python program executes line by line until it hits a GPU kernel call, in which case that kernel gets compiled then and there. This happens through a series of compiler passes, so it goes through the Triton frontend, MLIR passes, and finally a GPU-specific backend to get compiled to an executable that runs on the GPU that we are targeting. So to go through a code snippet with line by line, we have a Python program, and it starts as a Python program that executes line by line through the Python interpreter. Notably here, we define a grid, which is basically a 3-tuple of integers, defining the number of threads of execution, or what Triton calls program instances that run in parallel on the GPU, and this is a fairly standard thing for GPU kernels. Eventually, the kernel call is hit. The kernel is basically a Python function annotated with an annotation triton.jit. And this is how Triton tells when to trigger JIT compilation and also when to offload the execution of the function to the GPU. So JIT compilation happens, and the body of the kernel is offloaded to the GPU, where it executes in SPMD fashion. So what this means is that each program instance runs the same code in parallel. However, each of them are given different PIDs to distinguish between what work each of them does. And yeah, just to note here, the user defines the number of program instances at the beginning and passes it into the kernel when it's called. Finally, when the kernel finishes execution, control returns back to the Python interpreter, and the Python program executes as normal. So now you may be wondering, what does a programming error look like in a Triton program? The program we looked at in the previous slide actually contained a data race. So what's happening here is that we are defining a tensor of size 256 and also 128 program instances that are writing to this tensor simultaneously. The first instance writes to indexes 0 and 1, the second to 2 and 3, and so on. However, the programmer here accidentally set the block start on line 7 to 0. And what this means is that all of them are trying to write to indexes 0 and 1 simultaneously, which is a data race. The data race itself occurs on line 14, which is the write statement to the tensor. Here's another example, but with buffer overflow. Here we're defining a tensor of size 3 and 2 program instances that are writing to that tensor. The first one writes to indexes 0 and 1, second to 2 and 3. However, index 3 does not exist in this case. You can see where that is going. The error here is that the programmer set the mask to always true on line 9. And what this means is that each program thinks that its access is always within range, even though it might not be. And the buffer overflow itself occurs on line 14, which again is the write statement to the tensor. So these two programs that we went over are examples of what we call micro benchmarks. And a micro benchmark is a very small, minimal Triton program written by yours truly that exhibits a specific type of bug. And we use these two programs in conjunction with several others that we've written to evaluate the precision of our tool Triton-San, but we'll get to that later. First, let's talk about how Triton-San works. So here's an overview of Triton-San's workflow. Currently, Triton supports a variety of hardware platforms for offloading, including NVIDIA GPUs, AMD GPUs, and general purpose CPUs. Triton-San is enabled as an optional feature into a CPU backend called Triton Shared. And again, the reason we do this is because we want to leverage the existing LLVM sanitizers, which are built to run on the CPU. In order to enable Triton-San in our CPU backend, we use the sanitizer flags. And what they do is they tell the compiler to instrument or inject some sanitizer checks in your code during compile time, so that during runtime, both your compiled code and the sanitizer checks run, allowing these sanitizers to detect issues during runtime. So here's the workflow in more detail. The Triton kernel gets ingested first by the Triton frontend, which converts it to a Triton dialect, which is a very high-level dialect that is able to express the unique Triton constructs. We then introduce a custom MLIR pass that introduces some lineage operations, and lineage operations are operations like matrix multiplication and are found in both CPU and GPU compilers. At this point, we leverage the existing LLVM, built-in LLVM and MLIR passes to lower this all the way down to LLVM IR. At this point, we introduce the sanitizer flags and compile it to an object file. This object file is combined with a driver C++ script. This script is responsible for executing each iteration of the Triton grid. And all of this is combined into a single shared library, which gets loaded and launched immediately on the CPU through a Python library called importlib. So here are some other things we had to do in order to make this tool work. By default, the driver C++ script runs every iteration of the Triton grid in sequential fashion. So what this means is that no data races can occur and therefore go undetected. So in order to fix this, we parallelized the kernel execution with OpenMP, or more specifically, we gave each iteration of the Triton grid its own worker thread, allowing them to execute in parallel and therefore see data races. Note that this integration of thread sanitizer, which is our sanitizer used to detect data races, and OpenMP is nothing special, as it's officially supported through an LLVM extension called Archer. Another problem we were running into was that the errors we were seeing that were being reported by Triton-San did not seem very useful. If you got this error and you were the programmer of this kernel, you'd have no idea where this error is occurring. So for what we did to fix this, we added an MLIR pass to add debug information into the IR in the form of these DI attributes. And we made sure that they are persisted across all the subsequent LLVM and MLIR passes until at runtime, we are able to see more useful error messages like this one, where we have the file name and line number as well. Another thing we did was we make sure that the sanitizers are preloaded before the Triton program starts executing at all. And this gives the sanitizers a chance to initialize and do stuff like allocate its own set of memory called shadow memory to track execution metadata, which can be stuff like memory allocations or accesses. And this is how it's able to flag issues during runtime. We also register hook callbacks to intercept OS level APIs. So these are important API calls, like again, could be memory allocations or accesses. And finally, we have suppression lists that tell the sanitizer which non-Triton modules to ignore. So let's talk about the suppressions for a bit. In order to have suppressions, we use the LLVM's sanitizer's built-in mechanisms for suppression. So for example, for thread sanitizer, this looks like this. We pass it a suppressions file during runtime, and the suppressions file is basically a list of shared libraries that we want to ignore errors coming from. So why do we need this? When we were testing, we found that these third-party libraries were giving us some unrelated false positives that were detracting away from the important errors that were occurring from our Triton kernels. So we tried filtering these out by suppressing them, and Triton-San was still able to flag and detect the issues in our kernels that we are the most interested in. So, and this was the case in all of the micro benchmarks that we looked at. So basically, these suppressions function as a form of as a method to hone in on what's really important to the user, as in errors happening inside their Triton kernels. So evaluating our tool Triton-San, we use two data sets primarily. The first one is micro benchmarks, which we went over. The second is a set of more realistic cases with injected bugs. And these are kernels taken from the official Triton tutorial, and also a repository called TritonBench, which is a set of kernels typically used for benchmarking purposes and are somewhat more complex. We use both of these data sets to evaluate the precision and performance of Triton-San, where precision is defined by whether we were able to detect the bugs of interest in our data sets, and performance as in whether the memory and time overhead that we introduce into the runtime is reasonable. All right, so talking about precision first, we found that Triton-San was able to detect all of the issues that we were interested in the micro benchmark suite without giving us any false positives. As an example, this is a snippet from our buffer overflow micro benchmark. And again, the error occurs on the write statement, which is on line 25 in this case. And the error reported during runtime is that it's a buffer overflow, and it gives us the correct line number, which is what we expect. To put these results into context, we also evaluate the precision of another tool called Compute Sanitizer. And Compute Sanitizer is from NVIDIA and is actually Triton's officially recommended solution to detect these elusive programmer issues for Triton kernels running on NVIDIA GPUs. And like the LLVM sanitizers, they come with a suite of tools, each capable of detecting different types of programmer errors. And these are the 3 tools that we used because they correspond to the 3 issues that we were interested in. So here are the results. We found improvements in both the precision of detecting buffer overflow and data races for Triton-San. However, for use of uninitialized memory, we still haven't integrated that corresponding LLVM sanitizer that detects these issues into Triton-San, and would likely be a next step if we were to continue development. So here are the performance numbers. Of our 2 sanitizers that we do support currently, address and thread sanitizer, these numbers we found to be quite similar to other applications of address and thread sanitizer. So we think this is a good sign towards the usability of our tool. So for the remainder of this presentation, let's talk about some setup and usage instructions. On the right here, there is a QR code that links to the official README for Triton-San. So if you wanted to, you could just scan that and follow the instructions on there. However, we can still go over them briefly now. As mentioned previously, Triton-San has been integrated into a CPU backend Triton Shared as an optional feature, so you'll need to clone Triton Shared. And in this repository, we have a build script readily available for you. And what it does is that it installs compatible versions of LLVM, Triton, and Triton Shared, and also generates a script for easy invocation during runtime. So all you need to do is clone this repository and run the build script to install Triton-San. So say now that you have installed Triton-San and want to run it on a Triton program, what would you do? So the first thing you need to do is add these 2 lines to the top of your file. And what these do is that it tells Triton to use the CPU backend to compile your Triton code instead of like another backend like a GPU backend, because again, we want to run our kernel on the CPU. Since we are running our kernel on the CPU, we don't want to offload our tensors to the GPU, so we need to change those as well. And finally, we would invoke the sanitizers using this driver script Triton-San. And what you do with this script is you specify the sanitizer type. So we only support 2 modes right now, which are ASEN and TSEN, to detect buffer overflows and data races respectively. And following that, you just add the command you typically use to run your Triton program, which would be python program.py. Okay, so in summary, there has recently been a new trend in GPU-based, programming languages, and Triton is one of them. And we found that debugging elusive programming bugs in Triton is quite difficult, and there are limited tools and resources available. The ones that are available, like Compute Sanitizer, have limited effectiveness. So our tool's main idea, Triton-San, was to combine the LLVM sanitizers with Triton's CPU backend to precisely detect these elusive programmer errors. As a result, we saw improvements, making this tool a good addition to the debugging toolkit for Triton developers. And we also extended the LLVM sanitizers to be used on Python-based languages, which we think is pretty cool. All right, thank you for listening.
Hi, thanks for the talk. Did you find any kernels that could only run on GPU, so then you couldn't use your sanitizer with them?
That's a good question. Personally, we did not. However, our tool does have a limitation in that these kernels need to be compilable by our CPU backend, right? In order to execute on CPU, run the sanitizers. And we did find that some kernels cannot be, or were not supported by the CPU backend. So I guess next steps would be to continue development into the CPU backend, I guess, which is an open source one led by Microsoft to continue, I guess, expanding the efficacy of this tool.
All right, so I have a related question, which is, to my rather limited knowledge, at least some LLVM GPU backends have some sanitizer support. Have you explored using that?
So we've looked at the Triton documentation, and if you look at that page, like the options are really quite limited for Triton specifically. I think we covered Compute Sanitizer as the go-to sanitizer solution for Triton programs running on the NVIDIA GPUs, and we didn't find them to be all that useful. I believe there is one other solution mentioned in the official Triton documentation, but maybe I think it could be like AMD specific. I don't quite remember. Yeah, but unfortunately, we haven't looked into that yet.
Can you back up to the slide that compares with Compute Sanitizer? I didn't catch the differences. I just wanted to see that again. And also, can you comment, sort of following up on the last question about, like, I think you're saying Triton-San is an on CPU tool only. So contrast that with, like, say, Compute Sanitizer or other GPU sanitizers for on GPU debug. Are there any benefits there that you're not getting when you're running CPU only?
So that's an interesting question. I believe the logic for offloading to a CPU here is that we can leverage the LLVM sanitizers, right? And if it's just for the purpose of analyzing your code to detect these programming bugs, there is really like not that much difference because we don't care as much about performance, for example. We just care about being able to detect these issues, right? But this is an interesting question, and I'll definitely have to take this back to the team and think about that. I believe you also wanted me to comment on this table a bit more. So I guess here's an example of why it could be good to execute or to execute the bug detection on the CPU. If you look at buffer overflows, we found that Compute Sanitizer was only able to detect large overflows. And this goes back to what I said about memory allocation on the GPU and how it's typically much more than what a program needs. And we think this is what is causing Compute Sanitizer to be missing these buffer overflows. Whereas Triton-San, since it executes on the CPU, it uses allocation methods like malloc, which I guess results in a better way to detect buffer overflows. For data races, Compute Sanitizer just does not support any data race detection in, was it shared memory? Yeah. And Triton itself has its own constructs to support synchronization to shared memory. So like the programmer does not touch that at all, which is why Compute Sanitizer is not able to detect them, because they basically can't exist. However, data races and global memory still can, which is why Triton-San was able to detect them.
Okay, hi. Does Triton Shared have its own CPU backend, or is it reusing the CPU backend that's in the Triton Lang project? I'm aware of there's a few different CPU backends. I just was interested to know if it's its own brand new one.
So maybe I'm not the right person for this question, but I think it's a different one. I'm not too sure what it does differently specifically. This might be a question for someone else on the team.
So I think this question was already answered, but for the buffer overflow, for the example you ran, was there any other examples that you were able to find misses with detecting the large overflows in Compute Sanitizer?
So I think the large overflows were the main thing that Compute Sanitizer struggled with. If you're asking for like other cases that Compute Sanitizer was unable to detect buffer overflows in, can't remember off the top of my head. I don't think so.
Thank you. I see you're trying to like mimic the behavior of the GPU with the CPU. And like, isn't there any like true negatives or like false positives in your sanitizer?
Sorry, what was the question?
So if you try to like mimic the behavior of the GPU with the CPU, then it might be different, like because architecture is different and you're trying to like execute the GPU program with a different hardware. So I wonder is there's like some kind of like true negatives or like false positives in your Triton-San. It might not be accurate because you're trying to mimic the GPU.
Yeah, I think what you're saying is reasonable. We haven't really tested that with the GPU, so I can't give you like a great answer there. But I think it is reasonable that since we are like changing the backend where we're executing it, it would produce like different false positives. Like the behavior might be a bit different there.
Hi, thanks for the talk. It's really cool. I have a question. I see when you're doing the perf evaluation of the sanitizer, you compare like turning the sanitizer on and off on the CPU. But I was wondering if you have done any perf tests on like turning the compute sanitizer on the GPU versus turning the sanitizer on the CPU. Like, it's basically I'm wondering, have you ever encountered any kernel that's just too slow to run on CPU, or in practice it's usually fine. It will run longer, but it will give you better like sanitizer results.
So we did test with like the more complex kernels, like I mentioned, and for those that were supported by the CPU backend Triton shared, I don't think we found any performance issues, say. Does that answer your question?
Yeah, I guess it's just for you, it's not that slow that you can still afford to run sanitizer on CPU. Okay, cool, thanks.
Any questions? Right, so thank you.